We're now going to talk about simple harmonic motion. To help you understand what we mean by simple harmonic motion, let's look at a little example. What I have drawn here is a pendulum hanging from a ceiling. This point B is called the equilibrium or at rest position because this is what the pendulum would stop at if no outside force is put on the pendulum. Suppose we pull the pendulum back to point A and then release it. Assuming no friction, we're going to be able to describe the height of the pendulum as a function of time. We'll call the distance that the pendulum is to the left of the equilibrium point, and then we're going to describe the distance that the pendulum is to the right of the equilibrium point as a function of time. Let's watch what I mean by simple harmonic motion. The pendulum is going to go back to the equilibrium point, then to point C. Back to the equilibrium point, back to point A. Equilibrium, so on and so forth. So we're going to define some words now that are used in simple harmonic motion. The amplitude of vibration is the distance from the equilibrium position to its point of greatest displacement, A or C in the last example. The period of a vibrating object is the time required to complete one vibration or one oscillation. That is, the time required to go from point A to B to C and back to A. Simple harmonic motion is a special kind of vibrational motion in which the acceleration A of the object is directly proportional to the negative of its displacement d from its at-rest position. That is, the acceleration equals negative k times d, where k is a positive constant. If we solve this particular equation using advanced mathematics, we can find the formula for simple harmonic motion. An object that moves on a coordinate axis so that its distance d from the origin at any time t is given by either d equals a times cosine omega t or d equals a sine omega t, where a and omega greater than 0 are constants, moves with simple harmonic motion. The motion has an amplitude of a, absolute value of a, and a period of 2 pi over omega. One last word we need to define is the frequency. The frequency f of an object in simple harmonic motion is the number of oscillations per unit of time. Thus, the frequency is nothing more than the reciprocal of the period, that is, omega over 2 pi. So let's suppose that an object attached to a coil spring is pulled down a distance 5 inches from its rest position and then released. Picture in your mind what would happen. The object would oscillate up and down from that position. If the time for an oscillation is 3 seconds, write an equation that relates the displacement d of the object from its at-rest position after time t in seconds. Assume no friction. First, we need to understand that the motion is simple harmonic. The reason the motion is simple harmonic is because we're assuming no friction or other outside forces are going to slow the object down and bring it to an ultimate rest. When the object is released at t equals 0, we know the object is 5 inches below its rest position. In other words, d, its displacement when time is 0, is negative 5. Because of the fact that d equals negative 5 when t equals 0, it's easier to use the cosine function. In other words, we're going to say the displacement d of the object is equal to a times the cosine of omega t. The reason for this is because the cosine of 0 is going to give me positive 1, and then I can let a be a quantity such that I get d is negative 5. In fact, the amplitude of the object is going to be the absolute value of negative 5. So the amplitude of the object is 5. We were told that the period is 3 seconds because it takes 3 seconds for the object to go from down here. Let me just draw this. We let it go down here. It goes up past its rest position up here and then down to its rest and back. Up and back. Up and back. That's the motion of the object. It takes 3 seconds to go from here up to here and back down to here. Because the period equals 3, that gives us that 3 equals 2 pi over omega. That implies that omega is 2 pi over 3. So we have that A is equal to negative 5, and the value of omega is 2 pi over 3. We substitute those values in, and we get D equals negative 5 times the cosine of 2 pi over 3 times T.